Hello guys and welcome to the first part of the paper 3 data analysis questions. So let's get started. Here in this question, the equipment shown in the diagram was used by a student to investigate the variation with volume of the pressure P of air at constant temperature. You notice here that we're talking about the air, not the oil. The air was trapped in a tube of constant cross-sectional area above a column of oil. The pump forces oil to move up to the tube, decreasing the volume of the trapped air. The student measured the height of the air column and the corresponding air pressure. After each reduction in the volume, the student waited for some time before measuring the pressure. Outline why this is necessary. Well, of course, this is necessary because you need to wait in order for this system to have a thermal equilibrium to the surroundings. If you get it right away, if you get the measurements right away, then that means that the measurements that you will be getting may fluctuate or you may have fluctuations. So this is not really good for your graph. It's not really good for your data. So that means that you just need to wait so that you can see that the temperature is really constant for that period of time. So here, next. The following graph of P versus 1 over H was obtained. Alright, so we can see here that 1 over H as the x-axis and P is the y-axis. Error bars were negligibly small. The equation of the line of best fit is P is equal to A plus B over H. Determine the value of B including an appropriate unit. So we're looking for B. Notice that this is this line, but if we draw this line, this is starting from 0. So the y-intercept here is 0. The A here is 0. So in here, we can have P, which is, I will just choose a point. I will choose this point. So we can have P is 1 times 10 to the 5th is equal to, this is 2 2B. Again, 1 over H is equal to 2. So A is equal to 0. So therefore, we can say that B is equal to 5 times 10 to the 4th. You can also have this 2 times 10 to the 5th and then 4 as the 1 over H, and you will be getting the same answers. So basically, B is equal to P over 1 over H. Disregarding A, we say that B is equal to P over 1 over H, or P times H. So if that is the case, then we need to determine the unit. And how would we get the unit? So we have P times H is Pascal times meter. So we have Pascal and meter. However, we know that Pascal is also Newton per square meter, because remember that pressure is equal to force over area, and we know that Newton is kilogram per meter squared. So we have kilogram meter per second squared times meter squared in the denominator times meter in the numerator. So we can just cancel the meter and meter in the numerator and meter squared in the denominator, and we're left with kilogram per second squared. And that is the unit of this B. Outline how the results of this experiment in part C are consistent with ideal gas law at constant temperature. So that means that the constant here is the temperature, and how can we prove that this is ideal gas law? In the graph, we can say that the pressure is inversely proportional to the height. Again, the pressure is inversely proportional to the height. In the graph, in the system, we say that the volume is directly proportional to the height. Again, the volume is directly proportional to the height. So as the volume decreases, the height also decreases. So we say that in that, we can say that the pressure is inversely proportional to the volume, and that is the idea for the ideal gas law at constant temperature. So in constant temperature, we know that the pressure is inversely proportional to volume, which was stated in ideal gas law. I hope that it is clear. If you are not clear, you can look at topic 3, which is topic 3.1, which talks about ideal gas law. Next, last two questions. The cross-sectional area of the tube is 1.3 times 10 to the negative 3 square meters, and the temperature of air is 300 Kelvin. Determine the number of moles of air in the tube. So, we know that N can be gotten from the formula, which is PV is equal to nRT, and N is equal to PV over RT. However, we don't have PV. So we don't have volume, but instead we have the area. So what can we get? However, we know that the area, that B is also equal to P over 1 over H, or P times H. So what we can do is that we just multiply this height to the area. And remember that area times height is also equal to the volume. So we have B times A over RT. So 5 times 10 to the 4th, this is what I got from the first problem, times 1.3 times 10 to the negative 3 all over 8.31 times 300. The answer is 0.026 moles, and I will use 0.03 moles because I have 300 Kelvin, which is one significant figure. Next, last question for this first problem. The equation in B may be used to predict the pressure of the air at extremely large values of 1 over H. Suggest why this will be an unreliable estimate of the pressure. So if we increase 1 over H, then that means that it will have very small volume. Okay, it will have very small volume, and small volume means high pressure. In ideal gas law, it stated that the molecules are not close to each other, and hence the forces between them are negligible. So if you have a high pressure, remember that pressure is equal to force over area. So if you have a high pressure, then that means that there are greater forces acting on the molecules. However, this is not consistent with the idea of ideal gas law, which is they should not be close to each other and the forces between them are negligible. So this is the reason why this is unrealistic statement for this problem. I hope I get this clear so we can proceed on to the next problem.